Dawid Stachowiak, data scientist at deepsense.ai, and this presentation is about deepspeed, a high-level parallelism and memory optimization library. So let's firstly briefly discuss the agenda. We'll start with trying to understand what actually deepspeed is. Then we will move to the key feature of deepspeed, which is ZeRO. Then we will move to other features overview, which is some selected features which I found interesting, which are implemented in deepspeed also. And we'll end up with practical examples of usage. So let's start with understanding what actually deepspeed is. There are main goals of deepspeed, and we can say that these goals are the pillars of this library. In terms of training, this library focuses on speeding up the process, scaling it on multiple GPUs, and actually lowering the costs. In terms of inference, the higher pressure is put on the lowering the latency and cost as well. And if we talk about compression, the authors of the library mean squeezing the model size and lowering the communication overhead. So summing it up, we can say that the general purpose of this library is to democratize the usage of large neural networks. And let's stick for a moment with scalability. So authors promises us that the scalability can be even better than linear, which sounds pretty great. And it is actually achievable with ZeRO in its third stage with offload on. Actually, I will explain what does those shortcuts mean in a moment. But we can see already that the promises are pretty huge. So summarizing, deepspeed is a very minimalistic wrapper for a PyTorch code, and it allows us to use state-of-the-art methods of optimization and parallelization. And at the right, we have listed features which are implemented, the main features which are implemented in deepspeed library, which are distributed training with mixed precision, some of parallelism, like model parallelism, pipeline parallelism, the zero redundancy optimizer, which I will discuss in a moment, zero offload, sparse attention, 1-bit ADAM, memory and bandwidth optimization, and of course many more. So let's move to the key feature, which is ZeRO, and let's try to understand why it is worth to use ZeRO. So most of the techniques which involves data, tensor, or pipeline parallel has some limitations. And all of them, except the data parallel, needs significant, maybe not significant, but some model rewrite. And only by combining those three techniques, so combining tensor, the pipeline, and data parallelism, we can use such a big models and train them, train such a big models as 1 trillion parameters. So using ZeRO is actually possible only with small rewrite of our training script. It is actually a few lines of code. So after those promises, I think it is worth to try it. So ZeRO is a shortcut from zero redundancy optimizer, and it was introduced in 2020. It actually allows us to perform training on multiple devices in pretty easy way on multiple GPUs. Authors of paper, which is listed at the bottom of the slide, found out that the memory during data parallel can be optimized to tensor parallel efficiency while keeping the communication efficiency of data parallel. So on the image, you can see the baseline to which we will compare to, and it is a raw data parallel. So in the first stage, ZeRO, focusing on the partitioning the optimizer stage, which caused the largest memory footprint during the training, actually. And to show how big a saving is, let's imagine, for example, we would like to train a GPT-2 with 18 billion parameters on, let's say, 8 devices. And normally, optimizer states will take 80 gigabytes per device, but with ZeRO in stage first, it would be only 2.25 gigabytes. So it's already a pretty big saving. Second stage of ZeRO, extending the first one by adding backward pass partitioning. So we can partition the optimizer states and the backward pass states in the same time. Also, we can use activation checkpointing and offload those states to the CPU to even more benefit from this optimization. And the third stage of ZeRO, partition the rest of the listed states here. So now we don't have any redundancy, and the model parameters are partitioned also. And actually, now scaling of training such a model should be linear. And there you can see a comparison of all the stages, and I think you can see what is the magnitude of saving here. And almost a year later, so in 2021, ZeRO was extended by ZeRO-Infinity, which is described in the paper, which is listed below this image at the right. So ZeRO-Infinity breaks the memory limit by offloading training states to CPU or NVMe memory. Of course, those memories are much slower than GPU, but also orders of magnitude cheaper than it. So we can say that we trading the possibility of training such a giant model for a bit longer processes. And as you can see on this graph, if you have enough NVMe memory, you are able to run 1 trillion parameter model only on single V100 GPU, which actually has only 16 gigabytes VRAM, which sounds pretty absurd for me, actually. Of course, using offloading during training such a big model, it would require from us millions of computing hours, and it should be remembered that the ZeRO-Infinity exchanging the memory capability for slightly lower bandwidth, but for fine-tuning, for example, when we have a pre-trained massive model, it is absolutely acceptable to, since it not require from us that much compute time. So let's now talk about some other features than training with ZeRO. There is another feature which has ZeRO in its name, but it's not longer aiming to training, but inference. And by ZeRO-Inference, we can perform inference with models several orders of magnitude larger than allowed by classical approach. So when we try to fit entire model into one GPU, and it is possible because ZeRO-Inference stores the entire model in CPU or NVMe, and during the inference, it it transfers the weights of the model layer by layer to GPU only for computations. So we can imagine that it is a pretty good deal if we want to use a longer sequences or for example, bigger batch size. Because by keeping only one layer in VRAM at the time, the rest can be saved just for the input. So we can say that this technique is more throughput oriented, and probably if we have a case where the latency, which is latency sensitive, we shouldn't use it. We shouldn't use the ZeRO-Inference. Another interesting implementation available in deepspeed is 1-bit ADA, and it is focusing on optimization related to communication during training on multiple devices. And it is because the communication during training can be pretty expensive in terms of time. And in paper, which is listed at the bottom of the slide, authors describing optimization by compressing the Adams optimizer states. And actually, it is all based on the observation that the authors found out that Adams variance during the training is becoming stable. So at the beginning of the training, they running it classical approach like the one which is listed, which is showed at the right of the slide, and after some warm up, they changing the cycle of IDAM. So when variance finally converges to a stable value, instead instantly communicating the gradients of our workers, local momentum is updated with local gradients. Then we performing the compression and communicate that compressed momentum over all workers. So it would be much less communication overhead. And another great implementation in deepspeed is sparse attention, and actually it is the last feature which I will describe today. And sparse attention actually reduces quadratic memory of complexity of attention to complexity more close to linear, let's say, where W in this formula at the left depends on attention structure used. So to make this sparsity technique clear, at the right you can see the graph representing the dense matrix of attention, and there is multiple sparse graph representation available in deepspeed. And as an example, I will use the Big Bird, which was proposed by Google. So Big Bird was introduced in the beginning of 2021, and it's reducing the quadratic memory to linear. Authors of the paper, which introduced the Big Bird, have discovered that by combining the global attention, so the first matrix, which is represented on the image, it is a matrix attention which is computed by for some tokens in relation to all the other ones, and by combining this matrix with what's Stroga's graph, which is actually a combination of local attention, so all the tokens computed with their neighbors, and completely random matrix representation. And by combining those three matrices, we obtain the Big Bird structure, which actually achieving results close to dense attention, such in structure such in BERT model, for example. Additionally, because actually sparse matrix multiplications are not very well handled by today's GPU, as we probably know, their idea to calculate this attention is also pretty interesting. They introduced a method to do it, and the idea is to blockify the attention and change the order of the blocks to one that corresponds to sparse representation of attention, as you can see on the GIF. And actually, we can say that we still calculating it in a dense fashion, as our GPUs are used to. But as a result, we obtain the sparse representation. And now let's move to some practical examples of deepspeed usage. So actually, what we should change in our code to use deepspeed library. So, for example, if we want to train with deepspeed, we should call the deepspeed initialize method. We should provide the config for it, the model, and its parameters. And optionally, we can provide also training data as an argument. And then we will obtain training components, which is a model engine. It's a same interface as a PyTorch module, but it is prepared for parallelization. We obtain optimizer, training data loader, and learning rate scheduler. All of those components are set up based on the config which we're providing as an argument. And if we're talking about the config, it can be defined in the code. As well, we can define it in the JSON file. So it is very well documented how to prepare such a config in deepspeed library. In deepspeed library documentation. For example, this config, I think is pretty clear that it uses the zero optimization in third stage with offload. Also, it uses the half precision and 1-bit ADAM optimizer, which I described a moment ago. So everything else in the script actually should, for example, like training loop should be kept in an old way, and then we should run the script by deepspeed command instead of the Python command as we did normally. Deepspeed command has its own arguments, as you can see, the host file arguments, for example, there. This host file argument defining, in case of training on multiple nodes, it defining the IP addresses of the machines which we want to connect through SSH, and then run on them the script. And then we providing the name of our script and this script's arguments. In this case, it's deepspeed, which indicating the usage of deepspeed, and deepspeed config, which providing the JSON file to be loaded to initialization method. In case we're doing it on single machine, even the host file argument is not necessary, because we work in a local context. So deepspeed will already know that we want to use all the machines from all the devices from local machine. And now, if we're talking about the inference, I will just show you a very simple example, and I prepared a video for it, and I will just talk about this video. Okay. So it is pretty simple script. As external libraries in the script, I using only deepspeed. I using only torch module and transformers. So not many external libraries here. This script has arguments for batch size, data type, use deepspeed argument, which indicates if we want to use deepspeed or not. Then the model name. In this case, it will be Bloom 3 billion parameters input file, which I will show you in a moment, and a local rank, which is actually necessary to proper work of script which deepspeed will use. because deepspeed will override this argument and use it to indicate which device should perform computations. So there is an inference method, and simply I loading the tokenizer. I'm loading the model itself, and there is a line of code which actually make a difference. So only if we provide a use deepspeed argument, we will wrap our model to be prepared to parallelize by deepspeed. And there is an input file with 8 sentences which Bloom will finish up, and another pretty simple script to just show the GPU usage in real time. So let's firstly try to run the script in a classical way. So on the single card, which is the second one, and with a Python command. So as we do normally. As you can see, the initial allocation of memory started. We have to wait a bit for initialization of the model itself. And as we see, we are not surprised that the memory was not enough, only for on one GPU. And now we will try to use deepspeed argument to indicate that we want to use deepspeed inference. And the only difference is, as I said, usage of deepspeed command. And there is a pretty important one. So I will stop a video for a moment. We do not provide the CUDA visible devices environment variable as normally we do, because deepspeed command would override it. So we have to provide it by include argument, which is a deepspeed command argument. So I indicating that I want to use second and third GPU from localhost, and the only difference will be that I wrap up our model by deepspeed wrapper. And I will move video a bit. As you can see, as I said, CUDA visible devices were overwritten by deepspeed. And we are waiting for initialization of the model, and also for parallel backend, which is for, as far as I remember, NCCL. And it started. As you can see, the memory is allocated pretty equally, and yes, we got our 8 sentences finished up by Bloom 3 billion parameters. Some of them are better, some of them are worse, but it's actually all are the output of the Bloom. Okay, so okay, just a second. Okay. So yeah. So let's summarize our presentation. Now we know how deepspeed is capable to obtain linear scaling with minor chord changes. We got high-level understanding of what happening during the usage of zero redundancy optimization. We know how to use inference on giant models, even on single GPU. And we get familiar with some other interesting state-of-the-art optimization techniques, which can be used with the deepspeed library. So actually, it is all from my presentation, and thank you for the attention.